Welcome everyone. Today we're starting our investigation or our lessons on vertical projectile motion. We're looking at projectiles. This is such a nice section. It's based on equations of motion, which you've done previously, but now we're only concerned with stuff that goes up and down. We're not going to look at anything horizontally. So there's a couple of things you need to take note of while we do it. The equations won't be anything new. We just got to look at direction very, very carefully. All right? So this is where we're going to start. Why do objects that fly through the air have the same sort of motion? So why is it if I throw a ball, the ball will go up and then come down? If I throw it upwards, it's also going to go up and then come down. If I have a gun that's fired up into the air, the bullet will go up and then it comes down. And they always go on this little arc, okay? They always have like that sort of motion. We're going to ignore that arc motion, and we're only going to consider objects that go straight up and straight down. But there's lots of things that's common about that motion. Let's see what those are. We need to define a couple of things as we start. Then we're going to look at the equations. We have to talk about acceleration due to gravity, because that's really important. Then we're going to do graphs, and I can hear the groans. And then lastly, we're going to look at bouncing balls. Bouncing balls really just brings everything together for us. What are our keywords? Vertical projectile motion. What is that? Acceleration due to gravity. Oopsie, wrong way. Oh no, those are our keywords for today. Definition. Here we go. We're going to have to define what is a projectile. Where does it go? What does it do? What is free fall? And what is the difference between the two? And then, of course, terminal velocity. Those are the three definitions we're going to need to look at today. We then need to look at the equations. Those equations are given to you on your information sheet, so there's no excuses. Okay, you have worked with all of these before. It's just one little difference in one of the symbols, but they're not going to be anything new. And then we need to look at acceleration due to gravity. And the thing with acceleration due to gravity is that it has a direction that's always down, and it has a value that's always constant. Those two things are pieces of information that they expect that you know. They're not going to give it to you. It's something that's just known. It's an implied piece of information. Now, let's consider something. Have you ever thought about how is a skydiver able to control their motion as they fall to the ground? Personally, jumping out of a perfectly good working aeroplane does not appeal. But if you've ever watched skydivers, and if you've ever watched professional, they group skydive, and the skydivers all go in a group, and then they make funny shapes. There's whole competitions with it, and they make shapes. But somehow they're able to control the way they fall. That's quite impressive. All right, so let's see if we can get to some answers. First of all, let's define some things. The first thing we're going to define is what is a projectile. Okay, so a projectile is any object that is being thrown up, projected, or dropped. Thrown or projected, we're good. That's a projectile, because that's how we use it in English. Dropped feels a little strange, because when we drop something, it doesn't feel like a projectile. But in the science terms, it is a projectile because it has vertical motion. It's moving down. It's moving through the air. Okay, that's what makes it a projectile. Then we get free fall, and this is the definition that we struggle most with. Because an object is in free fall when this is very important, the only force acting on it is the force of gravity. This really doesn't sit well sometimes, because we hear free fall and we hear the word falls, so we think it means an object must be going down. Not in science. In science, when we talk about free fall, it's exactly what we said. It's any object that's moving through the air, but the only force on it is gravity. So when it's moving up, it's going to be slowing down, and when it's going down, it's speeding up. What this means for us is we are going to ignore air resistance. We're going to get rid of it. We're going to pretend it's not there because it makes our calculations simpler. That's the only reason. It's just to make it a bit simpler for school level. Go to varsity, we obviously add all of that in. We're just laying your foundations. Then we get terminal velocity. Now, this is what skydivers use. Terminal velocity is the constant velocity that a free-falling object eventually reaches when air resistance prevents further acceleration. In other words, we can only get to terminal velocity if there's air resistance. If we ignore air resistance, we will never reach terminal velocity. An object falls down, so an object falls because of gravity. While it's falling, air resistance moves up. When this force and that force are equal, the net force on the object is 0. And we know from Newton's second law that F net equals ma. If F net is 0, A is 0. It won't accelerate. And that's what skydivers use. When they jump out the plane, they might put their bodies all close together and small. That speeds up their motion. Then when they get to the height, when they're all at the same height, if you ever look at them, they lie flat, horizontal, and they put their hands out and their legs out, and that creates more air resistance. It slows them down. Okay, they're still going ridiculously fast, but it slows them down. And it's how all of them, by changing the shape of their body, can stay at the same velocity the whole way down. So they reach a different terminal velocity. Objects have to be thrown or dropped from fairly high to reach terminal velocity. So you're not going to reach it if you go to the third floor of a building and drop a stone. It won't reach terminal velocity. It's not high enough. Okay. Then we get to the equations. You've seen, all of these before. You've seen all of them. Vf is final velocity. Vf is measured in meters per second. Vi is initial velocity, also meters per second. Then we've got A. A is acceleration due to gravity. It is always 9,8 meters per second squared down. I'm putting a direction in it because whether it's positive or negative depends on the question, depends on our sign convention. Delta T is time, measured in seconds. Delta Y is vertical displacement. We'll just call it displacement after this, but I'm just trying to remind you that it's vertical. In maths, you know, you have the y-axis on a graph and you have the x-axis. Before, you worked with the x-axis, so you used delta x for displacement because it was horizontal motion. Now we're looking at vertical motion, we use delta y. So be careful on your information sheet. It gives you equations with delta y and equations with delta x. You must use delta y. We're going to work with these, okay? We're going to work with how to deal with those equations. Acceleration due to gravity, always acts down. You'd be surprised how many times I get told, number one, acceleration due to gravity disappears. Okay, it can't. We're on Earth, we experience gravity. And number two, that somehow it goes up. If acceleration due to gravity went up, nothing would ever come back down to Earth. I would be able to jump up and go to the moon. Okay, heaven forbid. That would not be a fun experience because we'd die in space. There's no air. But everything comes back to Earth. We are attracted to the Earth, so everything comes back down. The value is 9.8 meters per second squared down. This value you would have seen during Newton's law of universal gravitation. It's one of the things we can work out. It's not exactly 9.8, but it's good enough for our purposes to round it off. It's got several decimals to it. We just want to make the calculations easier, so 9.8's perfect. Once again, it's given to you. It's a piece of information on your information sheet. Last thing we're going to do before we take a short break is time symmetry. What this says to us is if I have an object that gets thrown up and then comes back down to exactly the same place, the time it takes to go up is equal to the time it takes to come down. They're going to use that often. So the time it takes to get to this point where it stops, so my velocity there is 0, is exactly the same to get back to where it started. The delta y in both of these are the same. So it takes a certain amount of time to stop and then the same amount of time to come back down. But it's got to start and stop at the same place. One last thing quickly. Over here, acceleration is still 9.8 meters per second squared down. At that point, at the top part of its motion, acceleration due to gravity hasn't disappeared. It's still there. It's what's making it stop and then come back down. If the acceleration due to gravity disappeared, miraculously, when it gets to the top of its motion, it would never come back down. It would sit there. Okay, be very careful. You'll get tricked out with this. So, lots of things to think about. We're going to take a short break, and then we'll dive into some questions. Welcome back, everyone. So we're going to carry on. Now we've got to start doing some calculations. I can hear the groans, but it really is okay. So let's just remind ourselves of the equations. I know we had them in the last one, but let's just remind ourselves. So here's our 4 equations. The thing about the equations is it's about making a decision as to which equation you need to use. There are lots of ways to look at it, so you're welcome to go, well, I would use the first equation. So over here, I'd use this equation when I don't have a displacement, okay? I use the second equation when I don't have, let's put this, when I don't know time. I use the third equation when I don't know VF, final velocity. And I use the last one when I don't know acceleration. So in reality, the last one you theoretically don't ever need to use because we're looking at vertical projectile motion. That means we'll always have acceleration as 9.8 meters per second squared down. You're welcome to learn this. The way I like to look at it is I will take my information sheet, I will look at the information I'm given in the question, and then, so for example, say I need to find delta t, I'd go, there's a delta t, there's t, and there's t. Then I start with the equation and go, what do I know? So if I knew VF, and I knew VI, and I knew A, then I know I can use the first equation. But say I didn't know VF. Then I know I can't use that equation. Then I've got to look at another equation, and I can come down to this one and go, well, do I know delta y? I know vi, I know a. I can use the third equation. Sometimes you may need to work something else out first before you can calculate something. So don't expect that every time you get one of these questions that you're only going to use one equation. Sometimes you may need to use more than one. But that shouldn't be the first equation. That shouldn't be the first part of any question given to you. So this really is about taking a deep breath, reading our questions carefully, doing our signed convention, making sure we know what we've decided as our signed convention, and then working through it step by step. Your questions will always lead you. All right, they're not going to go and give you a 10-mark one question worth 10 marks. They won't do that. No matter how difficult they try and make the questions, they won't do that. It's step by step. Okay? So, let's do a problem. Here we go. A stone is dropped. Dropped is an implied piece of information. Dropped means that my initial velocity is 0 from the top of a building, hits the ground traveling at 45, so that's final velocity. Ignore the effects of air resistance. It's free fall. We're happy. They want the height of the building. For a lot of us, just reading this just feels like so much information. I like to draw some sort of sketch telling me what's going on, because it makes it easier for me to process all the information. They told us we have a stone dropped, so here's my building, there's my stone, initial velocity is 0 meters per second, it hits the ground at 45 meters per second, and that's all the information they give us, and they want delta y. At this point, we need to remember we're working with vertical motion. That means gravity plays a role, and I know that my acceleration is 9.8 meters per second squared. But I'm dealing with vectors. Vectors mean I need to choose a direction as positive. The logical choice here is to make down positive, because it doesn't go up and down, so just make down positive. So I'm going to put that there. Now we get to the fun part of having to make a decision. I always write a list in this order. Everyone's different, but if you look carefully, this first part here, that's the first equation. VF equals VI plus A delta T. It's just what I've done over the years. It's just second nature. It really doesn't matter what you do here. My final velocity is 45. My initial velocity is 0. Acceleration due to gravity is 9.8. I don't know time, and I want delta y. If you go back and look at your equations, now you've got to make a decision. So let's quickly go back to the equations. We had, all right, let's just get rid of everything I've got here. So we had VF, we wanted delta y. Okay, so I want delta y, there's delta y, and there's delta y. I know VF, great. I know VI, great. And I know A. Oh, look, that would be the most logical equation. I don't know delta T, I don't know delta T, I don't know delta T. Equation chosen. So let's go back. I'm going to use VF squared equal to VI squared plus 2A delta Y. VF is 45. VI is 0. 2 times 9,8. So we have 45 squared, which is 2,225. Definitely can't do that in my head. We're going to have 2 times 9,8. Okay, which is 19,6. I need delta y on its own. So we're going to go 2025 divided by 19.6. And I get 103,32. Remember, we round off to 2 decimal places. It's a final answer. So 103,32 meters. Now, I'm working with vectors. I'm not putting a direction on this. They wanted the height of the building. That's a scalar. They didn't want the displacement of the object. They wanted the height of the building. You could always put a little note here now if you want it to be on the safe side and go, therefore, the height of the building is 103,32 meters. That's fine, but I don't need a direction because height is a scalar. We got it? Hopefully. Let's carry on. Come on. Oh, it's on that side, that's why. Okay. We're going to take a short break because there was a lot to process. And when we come back, we're going to do a couple more questions. So I'll see you in a couple of minutes. Welcome back. Now we're going to do some equations. So we did one beforehand. Now we're going to look at ones where we mix it up a little bit. Okay, so it's not quite as simple. We're going to add some things in where direction is important, but we can do this. Here we go. First question. A ball is thrown upwards at an unknown initial velocity. So we don't know VI. It takes 3,2 seconds to reach its highest point, and then they ask us to ignore the effects of air resistance, which is great. They'll do that with all of them, and they want VI. Right. Let's draw a diagram. Here we have my object, the ball. It throws up, and it gets to here. What they tell me is I don't know initial velocity. They do tell me, though, that it takes 3,2 seconds to get to the top. We now need to sort out what is the implied pieces of information. The first one is this. My final velocity is 0. It's reached the top of its motion, and it's about to come back down. We know acceleration due to gravity is 9,8. But that's down. Ooh, that should be a 2. But that's down. We need to make a decision as to what is our positive direction. I always take initial direction of motion as positive. If I take up as positive, that means this acceleration is negative. We like a question like this because hopefully you can already see if I go VF is 0, VI is what I'm looking for, A is minus 9,8, and delta T is 3,2 seconds. This is nice. It's the first equation. It's the easiest one to use. So we know that VF equals VI plus A delta T. VF is 0. We want VI. That's minus 9,8 times 3,2. We definitely need to put our calculators in this one. So we've got 9,8 times 3,2, and that gives us 31,36. Whoopsie, I didn't mean to do that. Let's go back. No, that's 0. 31, and that's a minus. It's always important to write it down properly. We want VI on its own, so when we swap it all around, but it's a vector. We got a positive answer, which was expected because I took down as negative, I took up as positive, it was thrown up. So this is up. Not so bad. Let's see what the next question has for us. Now we have things that are slightly different. Now they say a ball is thrown upward from the top of a building, of a 30-meter high building. The ball takes 2,4 seconds to reach its highest point. You must read these times carefully because a lot of you are going to read this and go, that's the time it took to get to the ground. It's not. So here's the building. It gets thrown up and it takes 2.4 seconds to get to here. Then it goes down. So I don't actually know the total time. Then they ask you, calculate the velocity with which the ball left the thrower's hand. In other words, initial velocity. And then calculate total time. We're going to show you a trick to that. Here we go. First thing that we've got, here's my building, which is 30 meters. My ball gets thrown up. It takes 2.4 seconds to get to this point before it comes down. This first part of the question is exactly like the question we've just done. I want initial velocity. I know the final velocity, which is going to be 0 because it's at the top of its motion. We know acceleration every single time, 9,8 meters per second squared down, and I know time. Nice and simple. What do we need to make a decision about? Sign convention. I'm going to take up as positive. I know my final velocity is 0. My initial velocity is what I'm looking for. My acceleration is now going to be minus 9,8. And my time, 2,4 seconds. Same equation we just used. So VF equals VI plus A delta T. VF is 0. We want VI. This is minus 9,8 times 2,4. Absolutely need a calculator. Let's get rid of that. 9.8 times 2.4. And it's 23,52. Oh, only one. There we go. Let's just not put an equal sign. I get very excited. Now I can't remember the answer. 23,52. Therefore, this is going to be 23,52 meters per second up. Please don't expect that every equation of motion that you're going to get in this is going to be some sort of trick, because it's really not. Okay, look at the mark allocation. This is only worth 3 marks, means 1 equation. Let's get to the next one. Now they want the time it takes for the ball to reach the ground. So we remember we've got 30 meters here. We've just worked out that the ball's going up at 23,52, if I'm remembering correctly. There we go. And we know that it takes 2,4 seconds to get here. And now they want the total time. This is where vectors become very special because of our sign convention. So we can't change the sign convention. This question would only be worth 3 marks. So I'm going to show you one way to do it, and then I'm going to show you another. We can do this in one step, in one equation. And it's about your convention. So up was positive, and they want to know what's the time when it gets here on the ground. I don't know what that final velocity is. I also don't know what this full distance is. But what do I know? So if we look at this, we've got VF, we don't know it. VI, 23,52 meters per second, and it's up. A is minus 9,8. Delta T is what I'm looking for. Now we've got to discuss what delta Y is. We said up is positive. Anything that goes below my starting point is negative. Over here, this is my starting point. That's my 0 line. Anything that goes above it, so any displacement above that is positive. Anything below it is negative. This is minus 30. That's the big thing here. That's very much the big thing here. So here we've got to pay attention. We now look at this and we go, it's not the nicest equation, but we can use it. Because now we can use delta Y equals VI delta T plus a half A delta T squared. We have minus 30. We have 23,52 times delta T plus a half times minus 9,8 times delta T squared. And right about now, the wheels fall off. Now we look at this and we go, that's impossible. No, it's not. This is remembering some stuff from maths. You're now going to have to use the quadratic function equation, okay? So we've got minus 30. This is 23,52 times delta T minus 4,9 times delta T squared. If I manipulate this, I'm going to get 4,9 delta T squared minus 23,52 times delta T minus 30 equals 0. Now it looks like a quadratic. Now it looks like an equation you've used before. If you get to this point in an exam and you look at that and you go, yeah, I can't remember how to solve those, because you just can't. You know what? Leave it. It's 1 mark for the answer, okay? It's 1 mark for the answer. You've got the signs. At this point, I'm going to remind you, I just need to rub some stuff out so that I've got space. So if we go here, I'm going to remind you what the quadratic function looks like, because we know we don't always remember it. And unfortunately, it's not going to be given to you on your information sheet. So you remember from maths that the quadratic function is this, that x would be equal to minus b plus or minus square root of, this is why you've got to remember it. I do remember it, b minus 4ac over 2a, okay? So when we look at this equation, 4,9 is a, minus 23,52 is b, and minus 30 is c, and delta x is x is delta t. So if we substitute it in, we're going to have minus 23,52, because it's negative, plus or minus the square root of minus 23,52 squared minus 4 times 4,9 times minus 30. Okay, and I've gone over, this is very badly laid out, with 2 times 4,9. The first thing you need to take note of is if that underneath your square root bracket, underneath that, if that ends up being a negative value, you've made a mistake, because you know you can't take the negative of a square root, okay, square root of a negative number. That's the first thing. From here, now it's all a maths thing. I'm going to solve what's in the bracket first, because I want to get rid of that square root, not the bracket, the square root. So I've got, let's do it this way, minus 23.52, oh wait, I've got it twice, let's not do that, minus 23.5, whoopsie. I can use the calculator, squared, minus 4 times 4.9 times minus 30. And I've got 1,141. It's a positive number, and I'm actually going to take the square root of this straight away because of space. I'm going to take the square root of that answer, and I get 33,78. So this has become 23,52 plus or minus 33,78 divided, and 2 times 4,9 is 9,8. Straight away, I'm hoping you recognize that I'm not going to go 23,52 minus the 33,78, because that's going to give me a negative answer. Watch, okay, just in case you don't believe me. So if I go 23.52 minus 33.78, and then I divide by 9.8, I get an answer that is minus 1,04. So the first answer we could get is minus 1,04 seconds. Hopefully you'll recognize we can't have a negative time. That's silly. It's definitely not going to be that answer. Let's see what happens when we add them together. So we could do, so we've got 23.52 plus 33.78 divided by 9,8, and we get 5,84. Now that time makes sense to me because it took 2,4 seconds to get to the top of the motion, and now it's going to take more time to get to the bottom. So even this minus 1,04 doesn't make sense, because then it took less time to get all the way to the bottom than it did just to get to the top, okay? And I know that was quite difficult. You could do it, and I don't like doing it this way. You can work out the time it takes to get to there and there. That's 2,4 and 2,4, and then you can work out that little distance and add them all together. I don't like doing it that way around because there's lots of little places we can make mistakes, and you may need to just think about this one for a little bit, okay? That one was hard, but you've done a lot today. We've done the equations, you've done some definitions, make sure you learn them, and now we're going to need to go and take a break. So we're going to end there for today, and I will see you next time.